So now that we know about the gravitational potential energy, let's do an example that helps illustrate what we're looking at. So here, let's say that we have a rocket on the Earth. So here's the Earth, which has a radius r, Earth. This thing has a mass m, Earth. And our rocket is going to start somewhere on the outside. So here's my rocket. There's my rocket. So what I want to know then is what multiple of the Earth's radius gives the radial distance the projectile reaches if, for part A, the initial speed is 1/2 of the escape velocity. So v initial is equal to 1/2 what's known as the escape velocity. We'll talk about what the escape velocity is in just a second. And then part B, what I want to know is, again, how far is this thing going to reach if its initial kinetic energy is equal to 1/2 of the escape kinetic energy. So this is what we want to know. So how far is this thing going to reach? So if this thing is shot off with an initial velocity, this part, initial velocity is 1/2 the escape velocity. Next part, the initial kinetic energy is 1/2. So how far away is this thing going to reach? So what is r as some sort of multiple of the radius of the Earth? So this is what we want to know. So first things first, we need to talk about the escape velocity. So what is the escape velocity? So the escape velocity is, by its definition, the minimum amount of velocity that you need to be able to escape the surface of a planet, in this case Earth, and go all the way out here to spatial infinity and stop. So basically what I want then is our rocket to be here, where this distance here, r is equal to spatial infinity, so my final position is spatial infinity, but my final velocity is also equal to 0. So this is what we call the escape velocity. So the escape velocity is what velocity do I need here so that this thing is going to go all the way out to spatial infinity and have just enough fuel to make it there, so that this thing runs out of velocity and actually stops. So, first things first is let's determine what is this escape velocity. So let's use conservation of energy. So okay, we have the change in kinetic energy plus the change in our new gravitational potential is equal to 0. Again, as I said in the last video, here we're working completely in space, so we're going to assume that we have a vacuum, so there is no air resistance, anything like that. So here we want our final kinetic energy to be 0, right, because we want it to stop. Minus 1/2 the initial, which is the mass of the object, times that escape velocity squared. That's my initial. Plus my final gravitational potential, but again, my final gravitational potential is equal to 0 because it's at spatial infinity, where we define then the final to be 0, minus the initial, which is minus a minus g times m, times the mass of the Earth, all divided by the initial, which is the radius of the Earth squared. All that has to be equal to 0. Right? So again, this is the final potential, which is 0 because it makes it out to infinity, minus the initial, but again, this thing has a negative sign, and the two negatives make this thing a plus. Now this mass is the same as this mass, so let's go ahead and get rid of it. And let's find this for the escape velocities. I'm going to add this term to this side. These two things make this a positive. So finally what I get is that the escape velocity is equal to the square root of twice of g times the mass of the Earth divided by the radius of the Earth squared. So this is my escape velocity. So using that, we can now go to the part A. So with part A, what we want to know is how far is this thing going to make it where, again, it stops. So basically what's going to happen is we want our rocket to make it to some distance here, where, again, the final velocity is equal to 0. So again, using conservation of energy, say the change in kinetic energy plus the change in gravitational potential energy is equal to 0. Again, my final kinetic energy is equal to 0. But we know that our initial kinetic energy goes with 1/2 of the escape velocity. Right? So our initial velocity here is going to be half of the escape velocity. That quantity is going to be squared. Plus the final gravitational potential. Now in this case, my final gravitational potential is not going to be equal to 0 because it's not infinite distance away, it's some finite distance away. So it's going to be plus a minus g times m times the mass of the Earth divided by that distance r, minus then the initial, which is minus a minus gm mass of the Earth, all divided by the radius of the Earth squared. And all that's equal to, again, 0. Now again, this mass is the same as this mass, which is the same as this mass, so let's get rid of that. Now, if I square this out, this is going to be the same thing then as what? The escape velocity squared divided by 4. So this is going to be 1/8. So I get minus 1/8 of the escape velocity squared. Leave it that way for now. And then I get a minus g times m earth divided by r. And then I get a plus g times m earth divided by the radius of the earth squared is equal to 0. Now, from here, though, we know the escape velocity then is the square root of all this stuff. So if I square that, I just drop the square root. And then this 2 is going to kill off that, which is going to make that guy a 4. Right? So basically, let's go to this side. What we're going to get in this case then is what? So I get minus 1/4 of then g mass of the Earth divided by the radius of the Earth squared minus g times the mass of the Earth divided by the radius, plus g times the mass of the Earth divided by the radius of the Earth squared is all equal to 0. Now, since every term has a g times mass of the Earth, we can go ahead and cancel those out because it's equal to 0, so we can divide through. So these two terms are the same, so let's add those together. So here I'm going to get a 1 over the radius of the Earth squared minus 1/4 of the radius of the Earth squared, which is the same thing as 3/4. This time I'm going to bring the other side, so I get 1 over r then is equal to 3/4 of 1 over the radius of the Earth. Sorry, let's see here. Oops, sorry, go back to here. That shouldn't be a squared. We're doing potential, not distances. Sorry about that. Get rid of that squared. No squared there. That's just simply an r and an r. Sorry about that. So 1 over the radius. So finally, this says the distance it's going to make then is 4/3 times the radius of the Earth. So what this says then is that this is the radius of the Earth. This thing is going to make it a total distance away from the center of the Earth 4/3 times the radius of the Earth squared, which basically means it's only going to get an altitude of 1/3 of the radius of the Earth. At exactly half of the escape velocity. So good. So now let's look at part B. And sorry about that squared there. So for part B, basically everything's going to be exactly the same. So for part B, we still have the change in kinetic energy plus the change in gravitational potential energy is equal to 0. The only difference now is we're looking at 1/2 of the escape kinetic energy. Right? So in this case, my final kinetic energy is equal to 0 minus 1/2 of the escape kinetic energy plus then a minus g mass of the Earth times mass of the object divided by r plus g times m mass Earth mass divided by radius of the Earth is equal to 0. So the escape kinetic energy then is equal to 1/2 the mass times the escape velocity squared. But again, using that as my escape velocity, this 1/2 is going to cancel that guy, so this is simply going to be m times g times the mass of the Earth divided by the radius of the Earth. Since I have half of that, so this is going to be equal to minus 1/2 of g times the mass of the Earth times the mass divided by the radius of the Earth minus g times the mass of the Earth times the mass of the rocket divided by the radius plus g times the mass of the Earth times the mass of the rocket divided by the radius of the Earth is equal to 0. Now again, all the g, m's, and e's, all those are going to be the same, so all are going to cancel. Here I have an r with an re, so that gives me a half. So finally I get 1 over r is equal to 1/2 1 over the radius of the Earth, which finally means that r then is equal to twice the radius of the Earth. So if instead this thing were shot off with exactly 1/2 of the escape kinetic energy, this thing's going to make it a little bit farther. So instead of making it a distance of altitude 1/3 of the radius of the Earth, it's actually going to make it an altitude of the radius of the Earth. So in this case, the total center to center distance in this case would be twice the radius of the Earth. Again, the altitude in this case would be half the radius, or the radius of the Earth. So this is an example using conservation of energy for now the gravitational potential. So again, the only thing that's different is now instead of using mgh here or mgy, this is now going to be the full version of the gravitational potential. Otherwise, everything works out exactly the same. So it's still just conservation of energy. So it's still just changing kinetic plus changing potential is equal to work done by the non-conservative force. But again, in pretty much all of these problems, there will be no non-conservative forces. So it's always just going to be delta K plus delta U is equal to 0. So actually easier than we've seen before.